Hi, everyone. I'm Marco, and this is Peter. My main focus is vulnerability research, mainly on OS X, iOS, and Android, and especially sandbox bypass.
Hi guys, I'm Peter. My focus is mainly Windows kernel, but also focusing on other kernels, mainly Unix ones, because it's interesting to see the differences and similarities and learn from them.
So our talk today is about fuzzing. So this is the agenda for today. So we will first do a brief introduction to us and our team. And then we will talk about VMware fuzzing, and then Peter will talk about Win32K fuzzing. And then we will make some conclusion and we will take questions. So our team is called Kin Security Lab. Previously, we were known as Kin Team. And this year, we won the title of Master of Pawn at Pawn to Own. And we are actively participating in this competition from 2013. And we have put some link to our blog if you want to check it out. So to summarize our talk is essentially about fuzzing. Especially we will cover graphic related fuzzing. So now we will start focusing on talking about VMware workstation fuzzing, fusion fuzzing. So I assume everyone here knows what is VMware workstation. So basically VMware was the first company to virtualize the x86 architecture, even before there was virtualization support at CPU level. Because the x86 architecture is not formally virtualizable. And but nowadays some instruction in the CPU were added, and so thanks to the VTX support, now it's much easier to virtualize this platform. And basically with VMware you can run a unmodified operating system as guest, so you can have multiple operating system running inside your desktop. This kind of software runs at different privilege level. Basically, they have a kernel component that does the virtual machine monitor, and then they have some user mode processes that maybe emulate some hardware or do similar operations. So in our talk, since the main topic of this talk is graphic, we will focus on how VMware virtualized the GPU, the graphic processing unit, and how they offer advanced functionality such as 3D acceleration, and how can we fuzz them and find bugs in this code. So why do we want to research on VMware? Well, because it's a very used software, and it's very attractive for some target, because maybe sometimes a virtual machine is used instead of your main operating system. And even if an attacker gains code execution inside of the virtual machine, it's still confined inside the virtual machine, so maybe it cannot take complete control of the underlying hardware. So we are still strapping into the virtual machine, and we want to find a bug in VMware that can potentially allow us to escape from the virtual machine guest to the host. So we want to escape from the guest to the host system. So there was some previous research and readings. The most important one is by VMware itself, where they describe how they implemented the virtualized GPU inside of VMware. So this paper must be absolutely read if you want to research in this area, because it will give you the basic knowledge to understand how to communicate with the GPU and how to do fuzzing. And the second one is a presentation in Black Hat, but by Kostya. And basically, it shows VMware Quest to host escape in the graphic driver. So it's a similar research to the one that we are talking about now. So about the VMware GPU, why they offer a virtualized GPU? Because thanks to Intel, the CPU is very well virtualized. Your code can run at native speed on your hardware if you have a VTX extension. But for GPU, maybe you can leverage VTD or some other new technology, but the support is not so good. So in order to offer good 3D performance and good general performance in graphic, VMware had to virtualize the GPU and to offer basically a fake graphic card inside of the VM. So in this way, VMware can also reduce the fragmentation and basically don't require any additional driver inside of the VM. So if you have a Windows virtual machine, you can find, you can look into the system property, and you will see you have this kind of graphic card called VMware SVGA 3D, which is a PCI device. This device is not real; it's an emulated device by VMware. And they provide this by having several memory ranges in the virtual machine, and these memory ranges are used to communicate with this artificial device. What about this memory range? There are two memory range. The first one is for the frame buffer, so just for the two-dimensional content. So it's not very interesting. You just draw your pixel in there. And the second one is a first in, first out memory queue. And this one is more interesting because in this queue you will write your commands that you want your GPU to process. And we are mainly interested into this first in, first out memory because it's more complex and more error prone. So you can think about this GPU and this queue about an asynchronous CPU running in parallel to your traditional CPU. So you just write your 3D commands in here, and you wait for the GPU to process them. So the first in, first out queue, when used for 3D commands, is some kind of protocol which is inspired by Direct3D APIs. So what you have to do to launch a 3D command is basically to write a command into the queue, and if you want, you can add a fence to be notified when this command is processed. And if you don't do that, you can just wait, and at some point the GPU will process your command and maybe do some 3D operation on the screen. So we are communicating with the GPU, but it's not very clear where this GPU emulation code resides. And actually this GPU emulation code is in the host user space. There is this VMware VMX process, which is also quite privileged, that runs outside of the VM, that will process these commands, and it will write the response back or maybe draw the screen. So if we want to fuzz VMware, we should, VMware GPU, we should expect crashes in this process. So what we want to do to improve our chance of catching bugs is to turn on page heaps in the global flags of Windows and turn on WinDBG auto start. So here is a summary of of the path of our code. So basically, we write into the virtual GPU, and then our commands will trigger some code in VMware VMX, and the VMware VMX will communicate with the host kernel, and the host kernel will use the real GPU. So it's quite a complex code path, and hopefully we can find some bugs. So this SVG A3D graphic stack is very rich of functionality because it accepts several type of shaders, several textures, and there is a lot of commands and a lot of attack surface. But how can we fuzz this? It's not very simple, like to fuzz some API or something like that. It's very low level. So we have to think a little bit more carefully. So we have three options. The first one is the simplest one, but it's also the most ineffective, is to fuzz the virtual GPU from the guest user mode. And but it's very inconvenient because there are several abstraction layers between our fuzzer, which is on top, and the virtual GPU, which is at the bottom. So let's think about it. If our fuzzer is running, it's using the guest kernel APIs. So this guest kernel APIs will do some validation, and we don't have explicit control on our data. And also we have some performance reasons because the guest kernel is usually using lock to prevent concurrency problems. So we cannot fuzz as fast as we want. And also we have some interference because our guest kernel is also drawing on the screen and using 3D commands. So even if we trigger some crash, we can have some noise in there, and we can have some problem to reproduce our bugs. So the other alternative is a little bit lower layer, and so basically it's to put our fuzzer in kernel mode inside of the VM. And in this way, we have more control. We can skip almost all validation and fuzz more properly. But there are additional problems because we are still running together with the kernel, and the kernel will also use the virtual GPU. So we have also an additional noise. And also, if you ever wrote kernel code, you have to be very careful to maybe, it's very easy just for a bug in your fuzzer to crash the OS. So finally, the solution that we take is the lowest layer possible. So basically, we just run a fuzzer without any operating system. And we just run this fuzzer on the bare metal, like on the virtual GPU. So in this way, we can also have a huge performance boost because our fuzzer now just need 4 megabytes of RAM. So we can just use maybe 50 VM or something like that, and we have complete control. And in this way, we have the best performance possible, less validation, and we can run a huge number of VM. So what do we want to fuzz? Because like I mentioned before, there was already some work by Kostya on the GPU of VMware. So the commands, to some extent, they have already been audited and fuzzed. So we finally pick two fuzz shaders. So because they are a very complex entity and a very complex format, so we can expect to find some problems in there. So what do we do? At first, we collect some valid shaders, and then we put together some code in our bare metal fuzzer to load the shader, render some 3D models with this shader apply, and then we mutate the shader, reload, render, check if it's crash, and then we start again and again and again and again until we get some bugs. So now I will show to you a demo of this GPU fuzzer. Like here you load a shader and you make this figure spinning, and after a while you will collect a crash. I will show to you also a demo of how a bug looks like. So basically here we are in VMware, and we are starting our fuzzer, which again it's very light. It takes only 4 megabytes of RAM, and then you will see. And the VM crash, and our page heap and WinDBG pop up, and we got a crash because VMware is executing a non-executable section. Oops. Okay, so soon we will post some CV in VMware Fusion because VMware is very slow. We disclosed this bug several months ago, but they finally decided to deploy the fix in Q3 2016. So we have to wait before publishing the details. And now I will give the microphone to Peter, which will talk about.
So I will talk about Microsoft's graphics. And in fact, because when you see that on Windows, a lot of fancy stuffs with picturing out the screen, you can imagine that it's a lot of code behind it. And with a lot of code, there is a lot of space for the bugs. One of the interesting vectors was past years in font. It was popular, especially in some sophisticated malware, and also abused by us at Pwn2Own last year. And also last year was really comprehensive fuzzing work done by Juru exactly on this topic, which results in a nice number of bugs. Windows graphics is not just about the fonts or about the data parsing, but it's also about the syscalls, which covers huge parts of the logic which you can mess with. And one part of the syscalls, let's say the graphics have multiple entities, so what to fuzz when it comes to syscalls. One can be DC, which is basically some screen when you can paint every fancy stuff you want. And very nice thing of DC is that it connects to many of different sub-objects, like a bitmap, brush, pen, palette, font, and region, and whatever else. And because of that, you can find a lot of, let's say, lines, a lot of some shapes, because it's connected all to DC. And because of this, it's really complex, it contains also some bugs. And I think after Pwn2Own, I have some work, but I remember that I have some bugs there, but I don't have time to process them. So after time, I think 2 months after, I go because someone improved the fuzzer and doing some other works, and I go back and running the fuzzer, but I cannot reproduce some bugs. And I was thinking, what's going on? And I was checking some acknowledgements at Microsoft, and then also Google project page, and I found that it's actually collisions. And as you can see, this one example of the bug, which is called if nils. It's about use of 3 in DC. And however, it wasn't only one bug, it was more, and so one of these bugs, one down the bug, was even better. I like it more. And it's handled user-free, also in DC, and this directly also in performing our fuzzing operations. Then I check the code of the POC, but because I have the bugs in the queue, but it was in form of crashes, so I don't get to making the POC. So for that, I was too lazy, and I was getting just for published POC. And as you can see, it's not too complex, but also not too easy. Because as we can show that it's I think about 4 objects, and they are somehow interconnected, each between themselves. As you can see, at first we create some DC, and this DC is then forwarded to creation of another object, its bitmap. And also this first DC is forwarded to creation of another DC, and the previously created bitmap is selected to this second DC, what was just created. And at final is providing as operation, which working on both DC, and that involves also bitmap and multiple connections between those objects. So that means, as I said, that in DC you can, and also in other objects and in Windows kernel, you can mess with logic that you interconnect a lot of objects together. And because the main purpose of fuzzing is that you do some chaos inside your target. And the one really good thing is that that chaos is somehow organized. It's not totally random, but it's somehow random, but it has some meaning. And especially, it's very, very good when you incorporate multiple objects to work together to make even more mess. And as I said before, that this is not only one object in the graphic, but another really huge object which have huge amount of syscalls is window. As Microsoft Windows, it's from name, and at this window you can see that it's a lot of syscalls related to just show some appearance of the window, move window, set some attributes to window, or send some messages to handling different events in window, some hooks, or also clipboard is connected to window, and other things. So it's really complex. And it's not enough. That's also that as you have window, it's window owned also DC owned, so you can find it also inside the window. So that means that it's interconnected with DC, and it offers also some APIs or syscalls to working closely with DC. So it can bring also under dependency, under mess to the fuzzing, which can be good for finding some bugs. And under some subject is also menu. It can be like entity alone, but it's deeply interconnected with Windows as well. And you can see with a lot of APIs, which is going as a parameters, syscalls with going parameters as menu and window together. So it's also very nice. And so as one of the example, it's for example bug like this one. Unfortunately, but also fortunately, this is not a security issue because it's just null pointer reference, which is in current state of Windows unexploitable. It's pretty good. And another thing, another area of the Win32K and fuzzing is that except some data parsing, like for example fonts or other things, and syscall fuzzing, which is in fact on content fuzzing context, and is there another thing, a huge one, is DirectX, responsible for huge amount of things. And it was previously discussed by under research, for example, the Blackheads by Ilya or by Nikita last year. And we also used one bug from DirectX this year for .1. And also DirectX we can divide to two different, two interesting parts. One of the most interesting is data parsing part. And as well, this is a really interesting one because it's not Microsoft code, but it's third-party code by graphic vendors, by Intel or NVIDIA. And it's a really huge amount of code. And that means, and it's not so properly written. And it works like that you have some, in Windows kernel, you have some functions which in fact allow to have more functionality through this custom drivers by these vendors. And basically, it's some kind of, these kind of methods are a nice example. That's because you, for example, on day3D empty escape, you provide some nice buffer, which is parsed for a lot of properties. And as you can see from past research of Nikita, there's a bunch of bugs, and still there are a lot. And the second part of the DirectX, it's not about data parsing, but it's about content fuzzing, about the syscalls again. But this area is not so fruitful because, for example, you can see that it's a lot of objects here as well, but those objects are in fact really easy. It offers only a few syscalls and don't maintain some huge state. You can find some bugs there, we found there, but it's not, I think it's not so fruitful. But it's interesting to go there anyway. And this code is directly by Microsoft. That means when you find bug here, you can pawn the Microsoft Windows and any hardware. It doesn't depend on your graphic vendor. So some words about fuzzing, how to fuzz these graphics. In fact, when you fuzzing the kernel, especially the syscalls, it's most likely be about the templates. That means you can fuzz fairly random, or you can add some let's say some rules, some borders based on knowledge, based on definition of the syscalls. And one nice example is syscaller, which is a fuzzer for Linux or Unix systems. And it have developed a very nice template system. And we also have in our fuzzer, we have something similar, but I have to admit it's not so advanced, this template mechanism like syscaller. But the idea behind is pretty much the same. And when it comes to templates, how to create those templates, one thing is you can reverse engineering, and second thing is that you can just, for example, go to check some documentation. Problem is that a lot of syscalls, mostly of syscalls, are not documented at all. But on the other side, why the syscalls? Syscalls is in fact just some layer, that is dark layer, but for programmers, it needs to be somehow to accessible, and it's for the APIs. And so in fact, APIs serve something like a wrapping. So in fact, what you can do is going just for documentation for APIs, and you can pretty easily to get those templates. But one not good thing is that APIs can be not just wrappers, but can have a lot of inside logic. But another thing, very good at this one, when you go to documentation and you understand those APIs, you understand how it works. So you have idea, and it's far more easier than to reverse engineer the real definitions of the syscalls in the kernel itself. But when you go for just for the APIs or just for what we are cover here, it's really just tip of iceberg. Because when you check properly on how much syscalls are in the Windows kernel regarding to Win32k, it's a huge amount, huge number, and not only related to this window or DirectX, it's a lot of different syscalls. So it's a really big attack surface. But on the other side, past few years, it's graphics is also improving. Microsoft Windows itself, and graphic is no exception. And there is a few reasons for it. So one of the reasons I like is that because of the cooperation of the different security researchers, security teams, that they find a bug and they responsibly disclose to vendor, to Microsoft, Intel, or the other vendors. And they cooperate to fix the bugs and really shrink the attack surface for the attackers. And that means that it's for the attacker, it's really harder to attack systems because when space of the bugs which are in fact available for you, it's shrinking, it's hard. And this number of bugs is not infinite. It's when you kill some bug, it's one over, and it's one less. So it's a really good thing. Another thing is that usually that when you write new code, you introduce new bugs, but it's not, let's say, equal. When you're killing the bugs, it's always really good and secure my platform a lot. And then the thing is that for example, Microsoft is not only doing the fixing bugs. It is the important thing, but it's not only one. Probably even more important is do some mitigations. And so one of those is, for example, then data parsing in kernel, and especially executing some instruction based on it. It's not a good idea at all. And so they stripping it from kernel back to the user mode. So even when there be some bugs, it's not affecting, it's not so critical. Another thing is that they process also starting some redesign of this graphic. And it's a really good thing, because when you redesign, you start thinking what is necessary, what is not, what is necessary to touch from the user, and what is not necessary. And it's when it's coming up the Win32K lockdown. What means that usually all the applications just don't need to access to these resources. So what they do, that from some strict sandbox, you can just restrict that these codes have no access to these syscalls, and therefore you strip attack surface. That's pretty good. And also they are fixing some old bugs, some leaking bugs, which it was past few years really popular to use. And now it's going to be fixed, so it's really great. And about the fuzzing, this is just some simple example of our fuzzer. It can be a bit different from the others because I'm early into C++, and that's the results. And how some fuzzing looks like from Win32K, we can show a quick demo. In fact, that I took just before I leave from home, and it just quick test for about 50 cores. And you see just some blinking of some different desktops. And basically, that's it. That's your goal, doing some chaos, and eventually running in some unexpected behavior. That's it. And now some words about OS X.
Yeah, we actually planned to talk about also OS X and iOS graphics fuzzing, but there wasn't really actually the time to do it, so we kind of left it out. But if anyone have any question about OS X or iOS, you can find us around and we can talk about it. But the approach and concept are quite similar for fuzzing. And we also did a number of presentations this year on this topic, if you want to check them out. The first one was at CanSecWest, and the second one was at Recon. And then in a few months, we will talk at Black Hat USA. And to understand how much important is graphic also on OS X and iOS in this year Pwn2Own. We compromised 2 times the OS X system, and for both the sandbox escape, we used a graphic bug. So this area of code is still rich of bug, and an attacker can leverage these bugs. So here's just a funny picture of my iPhone with the phone, the screen totally messed up by the fuzzing. And
And the reason why we use, for example, the graphic bugs at Pwn2Own, it was first that it's accessible from sandboxes and from the lowest level of the sandboxes. And second thing, that is huge surface, so it is all the bugs there. But on the other side, it's all the bugs there. It's questionable because it's recent years, and especially the last 2 years, this landscape is really shrinking down. And if introducing new mitigations, it's even more strict. So it's step by step is changing, and it's going really better. And with cooperation with many security researchers in this field, it's really improving. And it's also important to note that when you're fuzzing the graphic, you need to incorporate different approaches and principles, because it's different when you're fuzzing the core components of the kernel. And also that second thing is that in graphic fuzzing is two important vectors. It's data fuzzing and it's content fuzzing. And they are almost equal in graphic. So that was all from us. These credits to our teammates, our boss, and our colleagues, which help us with the research, and we can continue with our research very fast. So if you have any question, go for us. If not, okay.
You guys interested in looking at like the Zen VGA pass-through stuff, or is that just hardware enough that you don't think it's a real attack surface?
Oh, you mean the Xen hypervisor? Yeah, there was a really nice presentation at DEF CON or Black Hat some years ago. It was not related to graphics, but it was a KVM, actually, sorry, KVM escape. I personally haven't looked into that because we did this research on VMware some months ago, but now we are not keep doing it. But maybe in the future, if we continue to do research, probably we will take a look at other hypervisor, because now in security, in the next few years, there will be a rising trend for hypervisor, especially on Windows, and they will have an active role in the security of systems. So I think maybe in 2 years, we will see a lot of research on hypervisors, and so hopefully there will be more public research, and it will be easier also to start. Thank you for the great question. Oh. Sorry, can you repeat that? Oh, vSphere. Oh no, I never tried that hypervisor actually, but I think maybe VMware is reusing similar technology, so you can also fuzz that if you're. But I think maybe in an enterprise environment, maybe some feature are disabled because you don't need them, such as 3D acceleration. Maybe I don't think maybe it's too useful if you are running a bunch of server. So maybe you can just disable 3D acceleration and reduce the attack surface a lot. Because yes, basically in VMware the bidimensional functionality are simpler and just a frame buffer and few commands. But when you start adding 3D acceleration, you have a lot more of attack surface. But on VMware Workstation and the VMware Fusion, the 3D acceleration is enabled by default. So it's kind of a trade-off between security and performance for users. But for vSphere, I don't know if it's enabled or not by default. So I currently don't know this kind of hypervisor. So thank you for the question. If you don't have any other question, thank you very much. And this is our, oh no, sorry. If you want to follow us on Twitter, but I don't have our Twitter. Okay. Thank you very much.